Section 4.1, we're talking about triangle sum properties. Remember, the word sum means adding, and we're talking about a lot of basics with triangles today. So to start out, what is the definition of a triangle? It's a polygon with three sides. Remember, a polygon has to be a closed figure with line segments for sides. And to label a triangle, we would put letters at the vertices. So I'm going to label each vertex here, A, B, and C. And you can write that we have a triangle with a little triangle symbol, and I could write triangle ABC or really any order as long as I'm going around that triangle and listening to the three vertices. The big thing today, what is the sum of the three angle measures in any triangle? Sum means the total, or what do they add up to. So what do the three angles in any triangle add up to? And maybe you already know this, but you can do this at home. And actually, if you bring in a piece of paper having done this, I'll give you an extra credit point here for this chapter. But if you just draw a triangle on scrap paper or anything really, draw a triangle, put an A, B, and C in the vertices, like in the angles, cut out the triangle, and then either cut or tear the pieces apart. And if you put the angles A, B, and C all next to each other, you'll get this straight line. And now angles A, B, and C were the angles in the triangle, and you notice they're forming a straight line. You know the measure of a straight line is 180 degrees, so the angles in the triangle, once they're put together, add up to 180 degrees. And this leads us to our triangle sum theorem. Very important, you'll use this all year, that the sum or the total of the measures of the interior or inside angles of a triangle is 180 degrees. The angles in any triangle add up to 180. And this is just kind of a quick proof. You don't necessarily need to write this down, but you should be able to follow through with me. We're doing a quick proof of the triangle sum conjecture. Why do the angles in a triangle add up to 180? Well, I started with triangle ABC here, and I added in or drew in, it's called an auxiliary line when you put something else in a proof, but I drew in line EC so that it is parallel to side AB. So I'm going to mark these parallel. See, I drew this so that was the case. Remember last chapter we had a proof that from any point not on a line, there's only one line that's parallel to that line through that point. So I drew in that line parallel to this side of the triangle. And now one thing you know is that measure of angle 1 plus measure of angle 2 plus measure of angle 3 is 180 degrees. Notice where angles 1, 2, and 3 are. Of course those add to 180 because together they form a line. And we know a line or a straight angle measures 180 in total when I add those up. Also, I knew that EC was parallel to AB. I drew it that way. So this must mean that measure of angle 1 equals measure of angle 4. Take a look at where those angles are. Why is measure of angle 1 equal to measure of angle 4? Because of the fact that these lines are parallel. You notice this Z shape that we form when we do those angles. This is what we talked about all last chapter. We have a special angle pair off of parallel lines. Parallel lines always give us information about angles generally. And in this case, these are those alternate interior angles, opposite sides of the transversal. And between our parallel lines. So those are alternate interior angles. Also, measure of angle 3 and measure of angle 5 are equal. These angles are congruent for the same reason. We have parallel lines. It gives us information about angles. In this case, again, alternate interior angles. And it would be alternate interior angles theorem that would allow us to say, since we have parallel lines, those alternate interior angles are congruent. And now I'm going to do some substitution. Remember how we had 1, 2, and 3 added to 180 because they were on a line? Well, instead of angle 1, I know that angle 4 is the same. So instead of angle 1, I knew that measure of angle 1 and measure of angle 4 were the same. So I'm going to put measure of angle 4 here. I'm going to keep measure of angle 2 because that actually is an angle in the triangle. And now I have measure of angle 3 was the same as measure of angle 5. Again, alternate interiors. So instead of angle 3 here, I'm going to put measure of angle 5. Remember, these added up to 180 here. Now I know that angles 2, 4, and 5 add to 180 degrees. 2, 4, and 5 are the angles in a triangle. And yes, they do add up to 180. So a quick proof of the fact that the angles in a triangle add up to 180 degrees. And a quick example. One of the most basic things you should be able to do is just find a missing angle measure in a triangle if you have the other two angle measures. And there's a lot of ways to do this on the calculator. You could think to yourself, I know these add to 180, so you could be thinking, you could actually write out an equation. 30 plus 125 plus x, I know they should add up to 180. Or maybe you're thinking, well, I know what I have already. Right now, 125 plus 30, I have 155 degrees in that triangle. I just need that one unknown to add up to 180. So really you're doing 180 minus the total here, which is 155, and you find out that x is 25 degrees. Maybe some of you are thinking, well, I'm just going to take 180 and I'm going to subtract 125 and I'm going to subtract 30. It really doesn't matter what order you go about this or how exactly you find that angle measure, as long as you get familiar with finding missing angle measure in a triangle, knowing the angles add up to 180. This is an important theorem and a little different than what you might be used to. We're talking about exterior angles in triangles. So this is exterior angle theorem. Now if you notice, if I extend the sides of this triangle, I'm actually forming three different exterior angles. All three of these would be identified as exterior angles of a triangle because you basically extend one side and look at the angle outside of that triangle. I'm going to get rid of just these two and we're going to talk about this exterior angle in particular. What this theorem says is that the measure of an exterior angle, like this one, of a triangle is equal to the sum, or the total, of the measures of the two non-adjacent interior angles. So the measure of this exterior angle is equal to the sum, or the total, of the measures of the two non-adjacent interiors. This would be the adjacent interior angle. So I don't want that one, but these two would be the non-adjacent interior angles. Okay, non-adjacent interior angles would be here. So what this is saying is that the measure of this angle E is equal to the total of N and I, the two angles that are not next to it. I don't want the adjacent angle, but I know an exterior is equal to the sum of the two that are not next to it, the non-adjacent interiors. That's what this theorem is saying right here. And the reason why, I'm going to illustrate this here. I'm going to actually put where's that pen? Oh, sorry. There it is. I'm going to put that smiley face in there. The reason why is because this, I think, helps. We know that if I did E plus the smile face one, what would I get? Well, these two are linear pairs, so yes, they add up to 180, right? I also know that taking angle E, taking the three angles in the triangle, N and I and smile face, would also add up to 180. Because we just did that a few times. So N plus I plus my good old smile face, that also adds up to 180, right? These two add up to 180 because they're on a line. These three add up to 180, smile face, N and I, because they're the angles in the triangle. Well, if they both add up to 180, then these things equal each other. So that means in my next step, this is kind of like almost a mini proof, E plus smile face would equal N plus I plus that good old smile face angle. Because they both equal 180, they equal each other. That's like transitive property. And then if you notice, I can actually cancel out the smile face. Look at that, E equals N plus I. So any exterior angle or angle outside a triangle is equal to the two non-adjacent interiors added together. Let's do an example of that. Find each angle measure in the diagram. Alright, this angle is labeled as 70. It's an interior angle. This labeled as X, another interior. Actually, this 2x minus 5 is an exterior angle, isn't it? So you know that an exterior angle equals the sum of the two non-adjacent interiors. So N plus I is what I used in the last slide, but the non-adjacent interiors would be 70 and X. So I know that this exterior angle of 2x minus 5 equals 70 and X added together, 70 plus X. And now solve for X. I'm going to subtract X and get rid of it here. 2x minus X is just X minus 5 equals 70. I add 5 on both sides, and X equals 75. That means this is 75 degrees, because that's X. 2 times 75 is 150, minus 5 is 145, and if you notice, 145 does equal 70 plus 75. And even if I wanted to find this angle, I know these two should add to 180, so this would be 35. Or I know these three should add to 180, and they do then, if this is 35. Okay. Second example does not have an exterior angle, but we do need to find X. So you're thinking, these are the three angles in this triangle. What do you know about the three angles in a triangle? They add up to 180. So I have to add these up. 2x plus 3x plus x, and I know they should total or equal together 180 degrees because they're the angles in a triangle. In this case, the algebra asks me to combine like terms. 2x plus 3x plus another x. That's a total of what? 6x equals 180. Divide by 6, and x equals 30. That means this is a 30-degree angle. This is 2 times 30, or a 60-degree angle. This is 2 times 30, or 90-degree angle. And if you add 90 and 60 and 30, you do get 180, like we're looking for. Something else we need to do today is classify triangles by their sides, and then we're going to do by angles. Hopefully you are relatively familiar with these terms. When you talk about classifying triangles by sides, you're looking at if any lengths are the same. And you have scalene triangles, isosceles triangles, and equilateral triangles. Hopefully you know that a scalene triangle has no congruent sides. All the sides are a different length. If I wanted to draw an example of a scalene triangle, if I wanted to prove for certain that all the sides were a different length, I could put different numbers of tick marks on each side. Now an isosceles triangle, hopefully you know this one as well or have heard it before. Isosceles triangle, okay, technically it has at least 2 congruent sides, but generally you're thinking 2 congruent sides in an isosceles triangle. The only thing with this at least means if it has 3 congruent sides, it also can be considered isosceles, as long as it has at least 2 congruent sides. So this would be isosceles if those 2 sides were congruent. And equilateral, you should kind of know that because we know the term equilateral means that equal sides in this case, and so all 3 sides are congruent in an equilateral triangle. By the way, an equilateral triangle is also equiangular, making it regular. That's not a very good one. I apologize. Let's redo that. Alright, equilateral if all 3 sides are the same, and actually it is equiangular as well. So if you're told to classify a triangle by sides, it's either scalene, isosceles, or equilateral, depending on how many or whether there are any congruent sides. But we also classify triangles by angles. Now, in acute triangle, we know acute angles are less than 90, and to be an acute triangle, all angles less than 90 degrees. As long as every single angle is less than 90, it's an acute triangle. A right triangle has to have 1 right angle. By the way, you might notice I'm not being super formal with these definitions. I should say for acute triangle, it is a triangle with all angles being less than 90 degrees, but I think we have the idea. So a right triangle has 1 right angle. By the way, you might wonder, why are you saying 1 right angle? Why aren't you saying all right angles, or 2? Could you have 2 right angles? Well, we know the angles in a triangle add up to 180, don't they? So could you have 2 right angles? 90 plus 90 is 180. What would the third angle be? Okay, so there can only be 1 right angle in a triangle, otherwise you're over 180. And I mark that as a right angle there. And for the same reason, an obtuse triangle can only have 1 obtuse angle. There can only be 1 angle in a triangle greater than 90 degrees. Because of the fact that if you had more than one greater than 90 degrees, you're already over 180. Third angle wouldn't be able to be anything. So this angle definitely greater than 90, making it an obtuse triangle. And equiangular, we talked about what that word means. Equiangular means equal angles. So all angles are congruent in an equiangular triangle. And I mentioned that an equilateral triangle is also equiangular. Sorry, this one is equiangular, so I should be marking all the angles congruent here. 1 arc each. But an equiangular is also equilateral, therefore it is a regular triangle. And actually, you should be able to tell me the angle measures in an equiangular triangle. If these measures are all the same, that means I could call every single angle x, because they're all the same. And what do you know the angles in the triangle add up to? They add up to 180. So right now I have x plus x plus x equals 180. Well, that's how many x's? That's 3x equals 180. I do 180 divided by 3. The angle measures in any equiangular or equilateral triangle are always 60 degrees. Keep that in mind. You're going to see that over and over this year. So let's practice classifying triangles by angles and sides and drawing pictures associated. In this first example, I want to draw an obtuse isosceles triangle. If I want it to be obtuse, I have to have one angle greater than 90 degrees. If I want it to be isosceles, I need two sides congruent. So I need an obtuse angle and two sides congruent. How about I make the obtuse angle here, and I'm going to have the two sides I just drew be congruent. Now it's obtuse because of this angle, isosceles because of two congruent sides. And let's draw an acute scalene triangle. Acute meaning all angles are less than 90. Scalene meaning no sides are congruent. So I have to make sure all my angles are less than 90 and all the sides are a different length. That's pretty close to 90, but it definitely is less than 90, so I'm okay there. Got a little nervous at first. If it really is scalene, I should probably do different tick marks for every side. Alright. Another thing you should be able to do is classify a triangle from the picture. So classify by sides and angles here. Well, if I'm looking at the angles, I notice I have one right angle, making it a right triangle for sure. What about sides? Well, I have two congruent sides, and two congruent sides is called isosceles. So it's a right isosceles triangle. And what about this guy here? By sides and angles, well, all of the sides are marked congruent, making it equilateral. All of the angles are marked congruent, making it equiangular. And I mentioned before that if it is equilateral and equiangular, it is regular. And you should also remember, what does that make the angle measures? If all the angles are the same, if it's equilateral, equiangular, or regular, the angles have to be 60 degrees because 60 times 3 is 180. So classifying triangles as well. And one more sort of theorem. Actually, it's a corollary. And a corollary is an extra theorem based off of a previous theorem. So it's a corollary to the triangle sum theorem. It's kind of an extra tacked on thing that has to do with triangle sum theorem. Remember that this said that the angles in a triangle add up to 180. Well, I want to talk about specifically a right triangle and look at what do the acute angles of a right triangle have to be. The acute angles of a right triangle are what? The acute angles would be like 1 and 2 here. The one's less than 90, but if it's a right triangle, it obviously has a right angle. What do you know about angles 1 and 2? Well, if you think about it, of course you know that these angles add up to 180. The measure of angle 1 plus the measure of angle 2 plus, well, the right angle is 90 degrees, right? So you know that all three of those angles add up to 180. Well, what do I know about angles 1 and 2? I want to get rid of this 90 degrees. How about I subtract it from both sides, and 180 minus 90? I have 90 degrees left. Oh, look at that. So angles 1 and 2 add up to 90 degrees because that's the angle measures that are left in that triangle. And what is it called when two angles add to 90 degrees? You should remember that term, complementary. So in any right triangle, the two acute angles have to be complementary. They have to add to 90 so that all the angles in that right triangle add to 180, seeing you already have a 90-degree angle. It's just a corollary can help you solve for missing angles a little bit quicker, as we'll see in this example here. Find x. Well, it's a right triangle. I know this angle's 90 then. So using that corollary to the triangle sum theorem, I know these other two angles in the triangle have to add up to 90. Since all the angles add up to 180, of course I subtract 90, and look, they add up to 90, they're complementary. So I know that the 2x and the x minus 6, if I added those angles together, it would total 90 degrees. That's what's left for the angles to add up to 180. And to solve for x, 2x plus x is 3x. Minus that, 6 equals 90. Let's add 6. to both sides. 90 plus 6, 96. And then we do 96 divided by 3 on both sides. And we get x is 32. Which means this would be 64. And this would be 26. And they would add up to 90. Okay, so triangle sum theorem today and classifying triangles.